Students, in this video we are going to see improper integral of second kind. Definition is, let f be Riemann integrable in closed interval a plus epsilon comma b for all epsilon greater than 0 such that epsilon is lies between 0 and b minus a, but f is not Riemann integrable on closed interval ab. F is Riemann integrable in closed interval a plus epsilon. Okay, but it is not Riemann integrable on closed interval AB. Here choose f of epsilon is equals to integration from a plus epsilon to b f of x dx. Then integration from a to b f of x dx is said to converge to a if limit f of epsilon as epsilon tends to 0 plus a means what? If limit epsilon tends to 0 plus f of epsilon exists, at that time integration from a to b f of x dx is convergent. If this limit does not exist, then integration a to b does not convergent. This is the definition. In this definition, your f is unbounded at point a, and in this definition f is unbounded at point b. Let f be a Riemann integrable in closed interval a comma b minus epsilon for all epsilon greater than 0 such that 0 is strictly less than epsilon is strictly less than b minus a, but f is not Riemann integrable on closed interval ab. Let f of epsilon is equals to integration from a to b minus epsilon f of x dx. Then integration from a to b f of x dx is said to converge to a if limit epsilon tends to 0 plus f of epsilon is equals to a. If integration from a to b f is not convergent, then it is said to be divergent. Okay, this is the definition of convergence of improper integral of second kind. Now question is arises, what is improper integral of second kind? It is of the type integration from a to b. A and b are real numbers and f is unbounded at some point in closed interval ab. In this definition, f is unbounded at a. At that time, this is the definition for convergence of improper integral of second kind. And if in this definition f is unbounded at point b, so this is the definition for convergence of improper integral of second kind when f is unbounded at point b. Okay, see example. First example is, so that integration from 0 to 1 dx upon x is divergent. Okay, solution. Let f of x is equals to 1 upon x. F is unbounded at x is equals to 0. Okay, f is unbounded at x is equals to 0. If your integration from a to b, if f is unbounded at a, at that time f of epsilon is equals to integration from a plus epsilon to b f. Okay, therefore f of epsilon is equals to integration from, here a is 0, so 0 plus epsilon, to b is 1 upon x into dx. This is your f of epsilon. Okay, which is equals to, this is nothing but 0 plus epsilon is epsilon. So integration from epsilon to 1 upon x dx. Okay, integration of 1 upon x is log x, limit from epsilon to 1. This is nothing but log 1 minus log epsilon. Okay, apply limit on both sides. Limit epsilon tends to 0 plus f of epsilon is equals to limit epsilon tends to 0 plus f of epsilon. Okay, sorry, here f of epsilon is log 1 minus log of epsilon. Okay, Here log 1 is constant and it is 0. So as epsilon tends to 0, log epsilon is infinity. So this limit f of epsilon is infinity. Therefore, integration from 0 to 1 dx upon x is divergent. Therefore, this is divergent. Okay, very simple. Just you have to use the definition of convergence of improper integral of second kind. You have to check that this where that function is unbounded. Let us take second example. Prove that integration from 0 to 1 dx upon root of 1 minus x square is convergent. Okay. Solution. Here f of x is equals to 1 upon root of 1 minus x square. Okay. F is unbounded at which point? It is unbounded at 1. Unbounded at x is equals to 1. Okay. So f of epsilon is equals to, here, integration from a to b f of x dx. If your f is unbounded at point b, then f of epsilon is equals to integration from a to b minus epsilon f. Okay. So here integration from 0, 1 minus epsilon 1 upon root of 1 minus x square dx. Okay. Integration of this is sine inverse of 1 minus, this is sine inverse of x. Okay. Limits from 0 to 1 minus epsilon. Put the values of upper limit and lower limit. We will get sine inverse of 1 minus epsilon minus sine inverse of 0. Apply limit epsilon tends to 0 plus on both sides. Limit epsilon tends to 0 plus f of epsilon is equals to limit epsilon tends to 0 plus sine inverse of 1 minus epsilon minus sine inverse of 0, okay, which is equal to, as epsilon tends to 0, this term becomes sine inverse of 1, okay, minus, and sine inverse of 0 is 0. Sine inverse of 1 is pi by 2. So limit epsilon tends to 0 plus f of epsilon is exists. Therefore, integration from 0 to 1 dx upon root of 1 minus x square is convergent. Okay. Let us take next example 3. Prove that integration from 0 to 1 dx upon x square plus x raised to 1 by 2 is convergent. Let f of x is equals to 1 upon x square plus x raised to 1 by 2. Okay. This is a function integral from 0 to 1. So this function is unbounded at point 0. Okay. F is unbounded at point x is equals to 0. Okay. Actually, we prove this integral is convergent by using comparison test. Comparison test for improper integral of first kind and improper integral of second kind both are same. So we know that what 1 upon x square plus x raised to 1 by 2 is less than or equal to 1 upon x raised to 1 by 2. Obviously, x raised to 1 by 2 is always less than or equal to x square plus x raised to 1 by 2. If we take reciprocal, then we will get 1 upon x square plus x raised to 1 by 2 is less than or equal to 1 upon x raised to 1 by 2. Okay. Now means let here f of x is equals to 1 upon x square plus x raised to 1 by 2 and g of x is equals to 1 upon x raised to 1 by 2. Okay. Or just say here. Okay. Now see students, we have to show that this integral is convergent. Means what? By comparison test, we have to show that this integral is convergent. Okay. So this integral is also unbounded at point x is equal to 0. Okay. So limit epsilon tends to 0 plus integration from epsilon to 1. Here we will add epsilon in 0, so we will get epsilon to 1 upon x raised to 1 by 2. Okay. This integration is nothing but, or here we can say that g of epsilon is equals to what? Integration from 0 plus epsilon to 1 upon x raised to 1 by 2. Okay. So this integration is 2 into x raised to 1 by 2. Okay. Limits from epsilon to 1. Okay. So this will become 2 minus 2 into root of epsilon. Okay. Now apply limit epsilon tends to 0 plus g of epsilon, which is equals to limit epsilon tends to 0 plus 2 minus 2 into root of epsilon. This is nothing but 2. So this limit is exists, therefore integral from 0 to 1 g of x dx is convergent. Therefore by comparison test, what happens? Integral 0 to 1 upon x square plus x raised to 1 by 2 into dx is convergent. Okay. Now we will see p-test for convergence of improper integral of second kind. Okay. Theorem. The improper integral integration from a to b dx upon x minus a raised to p converges if p is less than 1 and diverges for p is greater than or equal to 1. This is the p-test for improper integral of second kind. What is the p-test for improper integral of first kind? It is the, suppose if the integral is of the type a to infinity 1 upon x raised to p dx, this integral is converges when when P is greater than 1 and diverges is P is less than or equal to 1. Okay. Next, comparison test. Theorem. We are not going to see proof of this theorem. We will see only statement and solve example based on it. Theorem. Let f of x and g of x be two Riemann integrable functions in semi-open at B, semi-open at A, semi-closed at B. Let f of x and g of x be positive. Let f of x and g of x be positive, and f of x is less than or equal to g of x in semi-open at A, semi-closed at B. Then first is integration from A to B, f of x dx converges if integration from A to B, g of x dx converges. And second is integration from A to B, g of x dx does not converge if integration from A to B, f of x dx does not exist or does not converge. See what is comparison test. Let f of x and g of x be two Riemann integrable functions in interval semi-open at A, semi-closed at B. Let f of x and g of x be positive, and f of x is less than or equal to g of x. Means we comparing f of x and g of x in interval semi-open at A, semi-closed at B. Then integration from A to B, f of x dx converges if integral g of x dx converges. If integration from A to B, g of x dx does not converge if integral A to B, f of x dx does not exist. This is a comparison test when f is unbounded at A point. Same comparison test for f is unbounded at B. Okay, there is no change. Okay. Similarly, this is a p-test for improper integral of second kind when f is unbounded at point A. But when improper integral is, when f is unbounded, here we can say that f is unbounded at x is equals to A. And when your f is unbounded at point x is equals to B, then your integral becomes integration from A to B dx upon x minus b raised to b. Okay, this keep in mind, students. Okay, these both conditions are same. There is no change. Only change is here. If your f is unbounded at point A, then your integral is of the type integration from A to B dx upon x minus a raised to p. And if your f is unbounded at point B At that time, integral is of the type integration from a to b dx upon x minus b raised to p. Okay. Now we have seen p-test and comparison test. Now see mu test. Here student, what is mu test for? Improper integral of second kind. Let f of x be Riemann integrable in intervals semi-open at a, semi-closed at b. If there exists a mu such that mu is less than 1 and x minus a raised to mu f of x is bounded, when x a is strictly less than x is less than or equal to b, then integration from a to b f of x dx is convergent. Second, if there exists a mu is greater than or equal to 1 such that x minus a raised to mu f of x has a positive lower bound when a is strictly less than x is less than or equal to b, then integration from a to b f of x dx diverges to infinity. In case it has a negative lower bound, then integration from a to b f of x dx diverges to minus infinity. Students, note that limit form of the mu test is more useful than the given in previous theorem. So we shall deduce the limit form of mu test. Okay, this is the limit form of a mu test. What is that? If limit x tends to a plus epsilon f of x into x minus a raised to mu is equals to L, which is neither 0 nor infinite, then integral from a to b f of x dx converges if mu is less than 1 and diverges if mu is greater than or equal to 1. If your f is unbounded at point A, then you have to apply this limit form of mu test. If your f is unbounded at point B, at that time you have to apply this limit form of mu test. What is that? If limit x tends to b minus epsilon, b minus x raised to mu into f of x is equals to L, which is neither 0 nor infinite, then integration from a to b f of x dx converges if mu is less than 1 and diverges if mu is greater than or equal to 1. Okay. Now let us write down next theorem. See, if f of x upon g of x converges to L as x tends to a, where L is neither 0 nor infinite. L is neither 0 nor infinite. Neither 0 nor infinite. Then the two integrals. Then the two integrals. Integration from a to b f of x and integration from a to b g of x dx either both converge or both converge or both diverge or both do not converge. Do not converge means divergent. Converge. Okay. If f of x upon g of x tends to S as x tends to A, where L is neither 0 nor infinite, then the two integrals, integration from a to b f of x and integration from a to b g of x dx. Either both converge or both do not converge. So we will see one example based on this theorem. Prove that integration from 0 to 1 sin x upon x square dx is divergent. Prove that this integral is divergent. Okay. Let f of x is equals to sin x upon x square. Okay. F is here interval is 0, 1. F is unbounded at x is equals to 0. Let us take g of x is equals to 1 upon x. Therefore, limit x tends to where your f is unbounded at point 0. So, limit x tends to 0, f of x upon g of is equal to sin x upon x square upon 1 upon x. Okay, this is nothing but sin x upon, here is limit x tends to 0, which is equals to limit x tends to 0. This is nothing but sin x upon x, and we know that limit x tends to 0, sin x upon x is 1. So here this 1 is neither 0 nor infinite. Therefore, integration from a to b f of x and integration from a to b g of x both here we directly can't say. Here we have to show that this integral is divergent. Integration from 0 to 1 upon x dx is divergent. Because see here, why this is because this is of p test. Here your f is unbounded at point x is equals to 0, and this is of the type x minus 0 raised to 1. Okay, this is since by p test. Okay, this is by p test. Okay, so by this theorem, limit means f of x upon g of x tends to 1, which is not equals to 0, and integral g of x dx is divergent. Therefore, integral 0 to 1 f of x dx is divergent. Okay, because both integrals divergent or both convergent. Okay. See students, how to solve this type of problem. Let f of x, find out where your f is unbounded. Let us take g of x. Okay. Choose g of x is equals to 1 upon x. Then we have to get limit x tends to 0. F of x upon g of x is equals to 1, which is not equals to 0 or nor infinite. And integration from 0 to 1 upon x dx is divergent. Okay. So by this theorem, in both integrals f of x and g of x converge together or divergent together. That's why integral from 0 to 1 f of x dx is divergent. Okay. See here students, if L is equals to 0 in this theorem and integration from a to b g of x dx converges, then integration from a to b f of x dx converges when L is equals to 0. If L is equals to infinity and integration from a to b g of x dx divergent, then the integration a to b f of x dx diverges. Okay. This theorem is where your axis tends to A. Means your x is unbounded at point A. Similarly, if your x is unbounded at point B, then your x tends to C. Okay, we will stop here. In next video, we will see some more examples. Thank you.